Hey folks, so we are going to be talking about chi-squared tests today, and specifically these tests are all tests of more tun one proportion. So we're doing a hypothesis test, but we're now doing it with 2 or 3 or 4 proportions and testing to see if they're equal to one another. This word chi-squared, let me get a pen. Chi-squared is Greek letter chi. It's lowercase chi. It looks like an X with a little squirrely, curly ends on each end, and it's squared. Has to do with the underlying distribution it was developed from. And we are going to be using some R code, so you may want to open that R code as well. So the chi-square goodness of fit test is a test of proportions when we have one categorical variable. And in this case, we're expanding the one proportion z test to 2 or more proportions. And so what we're talking about is when the answer to the question is not something that just has one level, it has multiple levels of answers. So instead of the house sold or it didn't sell, we might have uh, a situation like the child was below 5, between elementary aged, middle school aged, high school aged, or college aged. And so we may be grouping those things, into categories of ages that are not numerical because we're putting them in school aged groups. So when this happens, we are doing a chi-square test. By the way, this is what R was doing when we did the one proportion hypothesis test, but this is not a test that I can easily show you by hand without first showing you the normal Z test. And so that's why we start with the Z test. So we can expand the hypothesis test of one proportion Z test to testing 2 or more proportions of one categorical variable. We're testing that the variable of interest follows the proportions in the expected probability distribution function. So it's that probability distribution function that we're interested in. And it is no longer a binomial, which is what we had before. The chi-square test is used when the data are categorical and it measures how different this observed data is our sample data. So it measures how different our observed or sample data is from what we would expect if the null was true. So the expected. So we're looking at the difference between the observed and expected counts. So let's look at an example. A research question: is the proportion of original Skittles colors uniformly distributed, meaning are they all equal to each other? So our population of interest is Skittles, and we take a sample of Skittles from that population, and then we get the counts of each color, and then we use that sample to go back to the whole population to say if the populations are equal to each other. So the population proportion for each other, what we're interested in is the proportion of the population. So the proportion of yellows equal to the proportion of greens, equal to the proportion of purples, equal to the proportion of reds, equals to the proportion of, and I'm missing orange. So we're looking to see if all of the proportions of each of the 5 colors are equal to each other. And so we actually have to get p hat of orange, p hat of red, p hat of purple, p hat of green, and p hat of yellow for all of the samples. And we use that information along with probability rules that we don't do in this class to do this hypothesis test. We will not be doing confidence intervals in this particular module, but you can do confidence intervals after you do a hypothesis test. All right, so to develop the hypothesis test, we're going to need how we write the hypotheses, the conditions or assumptions we have to meet in order to use or do the test statistic, and the underlying sampling distribution of our test statistic, and specifically the formula for that test statistic. So remember that we are testing multiple proportions with this chi-squared test. So more than one proportion. The hypotheses, the null can be written in two different ways. So all proportions are equal to each other is the first way. That's called a uniform hypothesis. We're looking to see if each of the proportions are equal to each other, like it would be if you were rolling a die or flipping a coin. So example one, are hospital births equally distributed on days with a full moon and without a full moon? So the null hypothesis is that the proportion of full moon babies is equal to the proportion of not full moon babies. And then our alternative in this case is that they are not equal. So we don't do greater thans here or less thans, we just do not equal tos for this test. Example 2 has more than two proportions as the possible answers. Are hospital births uniformly distributed across the days of the week? So the null hypothesis is like the Skittles example. The proportion for Monday is equal to the proportion for Tuesday, is equal to the proportion for Wednesday, is equal to the proportion for Thursday, is equal to the proportion for Friday, is equal to the proportion for Saturday, is equal to the proportion for Sunday. And the alternative, because we're not saying that they are all not equal to each other, we don't write it similar to the way we did above. Instead, the alternative hypothesis is at least one proportion piece of I differs. And so what we're saying is that any one of these could be wrong, and then if one of them's wrong, by the way, two of them are almost certainly going to be wrong, but that's not always true. But let's say two of them are wrong and the other five are all equal to each other. So what we're saying is that at least one is different. All right. The other way we can write these hypotheses is all population proportions are equal to specific values. The sum of all the population proportions in the null has to equal 1 because it's still representing a PDF. So for example, when crossing homozygote parents expressing two codominant phenotypes, A and B, we would expect in the second generation that the null, the probability of getting A is 1/4, and then semicolon or comma, the probability of an AB is 1/2, and the probability of a B gene is 1/4. Notice that these all have different numbers, and AB is the intermediate phenotype. And then the alternative is written like we wrote it above, at least one proportion PI differs. Well, notice that we wrote this second way with numbers. We can actually do that with the first two. So the first one only has two proportions. So each of these proportions has to be equal to 1/2 or 50%. And so in the alternative, we're saying that they are not equal to that. For example, 2, there are 7 proportions, and so we're saying that they're each equal to 1/7. And for the alternative, we're saying that at least one of these is not equal to 1/7. All right. So now let's look at our test statistic. The test statistic is a chi-squared statistic. Unlike many tests, the chi-squared statistic does not follow that format, statistic minus parameter divided by the standard error of the statistic. So instead, the chi-squared statistic compares observed and expected counts, and this really has to do with the fact that we have categorical data. It's a measure of how far our observed counts or our sample data in a random sample are from the counts that we expect as defined by the null hypothesis. So, in other words, based on probabilities under the null. So, our test statistic is a chi-squared test statistic. And so chi-squared is equal to the sum of I equals 1 to k of our observed in parentheses minus expected, whoops, quantity squared divided by expected counts. So what's happening here is we take each of our observed values, the sample data, and we subtract off what's expected. But like standard deviation, we don't care if that value is too high or too low. We only care how far away it is. But again, absolute value causes problems with calculus, so instead we square it, and then we divide by the expected counts. All right, and so the short way of writing this, sum of the capital O minus capital E squared over E. So typically that's the way you'll see me write this test statistic. K is the number of outcomes the categorical variable can take on. So in our full moon or not full moon babies born, K was 2. In the days of the week example, K was 7. And in the F2 generation example, K was 3. O is our observed counts. These are the number of observations of each of the categories from our sample data. And the expected counts are the number of the observations we would expect to see for each of the categories if the null was true. We have to calculate the expected counts. And so the expected counts, let me move this up, that'll make it better. Counts is equal to n, remember n is our sample size, times the proportions in the null. So in the full moon, not full moon case, we'd be multiplying sample size by 1/2, and that would be the case for both categories. And in the days of the week example, we'd multiply n by 1/7, and the expected count would be the same across all 7 days. And then in the phenotype example, we'd have to do n times 1/2 and n times 1/4, and we'd have different expected counts for each of those categories. The larger the value of our test statistic, the chi-squared test statistic, the greater the average distance between the observed frequencies and the expected frequencies. And the large differences or large chi-square statistics equate to small p-values and favor rejecting the null. This distribution over here is a chi-square distribution. It is a positive distribution, meaning it starts at 0, and it is skewed right. And our chi-square test statistics tells us where we are on the x-axis. And then the area to the right of that is the p-value. This is the p-value, the area to the right of that. The sampling distribution is a family of distributions that take on only positive values. They're always skewed to the right and are described by the degrees of freedom. Large values of chi-square represent strong deviations from the expected distribution under the null and will be statistically significant. So this is worth writing or saying again. Large chi-squared values gives us small p-values. And remember, small p-values are when we reject the null. In the chi-square goodness of fit test with k categories, the test statistic has a chi-square distribution with k minus 1 degrees of freedom. And so the distribution changes, gets a little less skewed, right, as degrees of freedom get bigger. The conditions for the chi-square test of proportions, the random sampling of one categorical variable, and then technically the second condition is that all expected counts are at least one, and no more than 20% of these counts are less than five. I use a more conservative condition, but it's easier to satisfy, and that's that all expected counts are at least five. And that's what we'll use in this class just because it's easier to deal with. If you don't meet this condition, you can go back to the other condition. So we have random sampling, and all of our expected counts are greater than or equal to five. This is similar to our condition before when we were trying to satisfy normality, where we had to have n times p is greater than 10. So instead, we're looking at expected counts. And again, we're not using normality here, but it's similar in the way we think about it. We're still going to do the same 5 steps of the hypothesis test, but we're going to be adding a step this time. So you write your hypotheses in words or symbols, you collect your sample data, and you state or calculate all of the necessary given information and statistics, but you have to visualize your graph and data. So this is new. We didn't do it in the last section. And the reason we didn't do it is we couldn't graph our data in the last module because we had categorical data with only one level. So we need to satisfy our conditions, and then step 3 is to do the hypothesis test and calculate our test statistic and our p-value. We will do one of these by hand, but normally we'll do these using software R for us. Make a decision to reject or fail to reject the null hypothesis, and you state a conclusion about the alternative hypothesis. All right, let's do an example. We're going to do this example by hand using the chi-square table, and then we're going to do it with R. So according to Mars Incorporated, the proportion of each color in a Skittles bag is equal to 20% each, meaning it comes from a discrete uniform distribution like rolling a die. Conduct the hypothesis test to determine if there's evidence for or against this statement. Normally, I'd pass out candy and we would collect our data, but we're going to use numbers from last year's class. Because this class can't do that because it's online. All right, so questions to ponder. What statistics or numbers will we need? We're going to need our observed counts, or our sample data. Those are our OIs for each color. And remember, the test statistic is chi-squared is equal to the sum of the OIs minus the EIs squared over the EIs. And so we also need our expected counts. And these are the EIs for each color. And we have to calculate these. They are n times the probability, the proportion in the null. And then what graph will we need? We're going to need 2 of them. We're going to need a graph of our sample data. And we need a graph of what we expect. Graph of what we expect. And because this is categorical data with multiple levels, these are bar graphs. And then how are we going to satisfy the condition that all the expected counts are at least 5? Well, we have to show that all of the EIs are greater than or equal to 5. So we take n times each of our proportions in the null. Well, we're saying that they're each 20% or 1/5 of the colors has to be greater than or equal to 5 for each color. And just a quick reminder, if the proportions are not the same in the null, you have to calculate EIs for each value and category, like the phenotype example. Okay, so let's do our example. So I've already done the graphs in R, but we could do these by hand. I don't know who would. Okay, so here's the raw data. So I handed out Skittles and I randomly sampled people from the class. The Skittles came from multiple locations. We had 27 yellows, 23 reds, 26 greens, 34 oranges, 39 purples, and 149 Skittles. Now, clearly those numbers are not the same. The question is, are they close enough that it indicates the proportions really are the same in the population or in the true values of them? So our hypotheses. The null hypothesis is that the proportion of yellows is equal to the proportion of red, is equal to the proportion of green, is equal to the proportion of orange, is equal to the proportion of purple, and each of those is equal to 1/5 or 20% or 0.2. It doesn't matter how you write that. We do have to have numbers when we put this into software, so I don't typically use percentages here. And then because we have more than two of these, we write our alternative at least one, and we just use P sub I to say proportion differs from 1/5. So we do actually use the number there sometimes. You don't have to, though. You could have just said at least one proportion differs. And then our conditions, do we have a random sample? We did, in fact, take a random sample. You all don't know that because you didn't see the data collection. And then each of our expected counts has to be greater than or equal to 5. Let's do this one. So this is n times 1/5, and n was 149 times 1/5, which is 29.8. So the expected counts for each category is 29.8. And that, in fact, does meet the conditions. So we can do the chi-square test of proportions. All right, so if we were going to graph this data, and I'll show you how to do it in a little bit when we get into R, we would graph our expected counts for each of the colors. Our expected counts were 29.8, so I just put that into R as a variable for each color. And so I did a column of data of 29.8, 29.8, and so forth and so on. And I graph this data, and I typically use gray for my expected distribution. And then my observed or sample data, I use actual colors. In this case, I used each of the colors of the rainbow reasonably. You wouldn't typically use this many colors on a graph, but with Skittles, I think that's reasonable. And so when you look at the graph on the left, we expect each of the colors to have the same height bar. When we look at our sample, they clearly do not have the same height bars. The question is, are these bars far enough apart that you can assume or show that the population is not 1/5 for each color? By the way, I did expected counts on my y-axis. You can do proportions here. And for us, that would be 1/5 or 20%. We don't particularly care that these two graphs are on the same scale. What we care about is the shape of the graph looks the same. And so I don't care which way you do that graph. So we're going to do our test statistic, but we're going to do it by hand first, and then we're going to calculate it in R. So our test statistic is chi-squared, and I'm going to move all the way to the left because we're going to need a lot of space. Chi-squared is equal to the sum of k equals 1 to 5, because there are 5 colors, of the observed count minus the expected count squared over the expected count. And I don't care if you have the little sub i's there or not. Well, we just need to take this for each color. So our first color is yellow, and that's 27. So we do 27 minus, and remember our expected count is 29.8. So 27 minus 29.8, quantity squared, and then we divide by that expected count, which is 29.8. We will be using 29.8 in all parts of this problem here because the expected count doesn't change with each color. So now we need to do the next color, which is red. There were 23 of those. So it's 23 minus 29.8 squared divided by 29.8. And then we do this again for the next color, which is green. That was 26. So the observed is 26 minus expected, 29.8 squared over 29.8, plus next color is orange. So that's 34 minus 29.8 squared over 29.8. And I got to keep going. Plus the last color is purple, is 39 minus 29.8 squared over 29.8. And you got to put all of this into your calculator. By the way, this is a calculation error waiting to happen, as you can well imagine. I put all this in and I did 5.73. And this value here is my test statistic. And so we need to figure out, is this test statistic big? And if that's the case, it gives us a small p-value. So the rule for that is here in the text box. We won't normally need this, but we're going to reject the null if our test statistic is larger than the critical value from the table below, which is on the next page. The critical value is the value at which the p-value would be less than our level of significance. I didn't give you a level of significance, but for us, that's going to be alpha of 0.05 because that's the standard level. So our chi-square distribution looks like this. It's a skewed distribution on the x-axis. And I'm going to mark the x-axis starting at 0. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so 5.73 is right around here. So this is our p-value. And we don't really know if that's big or small because we haven't been working with the chi-square distribution. So what we use is these tables that have been built for us. This table, and I'm going to use purple here, gives us the p-value associated, or no, sorry, not the p-value. It gives us the probability, which is our alpha level. So we're using alpha of 0.05, and notice it says significance level alpha. Our K was number of categories minus 1, which is 4. So sorry, I did that wrong. Let me start over. Our degrees of freedom is the number of categories K minus 1. So 5 minus 1 is 4 for us. So our test statistic falls on the line where degrees of freedom is 4 and where it crosses at alpha of 0.05. So any test statistic bigger than 9.488 gives a small p-value and you reject TO. Anything smaller than that gives a big p-value, and you fail to reject Ho. So 9.488 is out here. This thing here is called our critical value, and it comes from the table. This is alpha. Alpha is 0.05. Well, notice that the area we shaded in orange is bigger than the area shaded in purple. And so because of that, our p-value is big. Our p-value is big. We don't know what it is. The rule is over here. This is the rule we're going to use. Chi-squared calculated, or test statistic, is bigger than the chi-squared from the table. And if that happens, you fail to reject Ho. And remember, when we fail to reject Ho, there is not evidence for Ha. There is not evidence to show any proportion differs from 1/5 or 20%, and that indicates the Mars distribution holds in the population. We wouldn't normally have to say that. I'm just going to say it here because we had that as our research question. So of course we can do R with this, and we're going to do it now. So real quick, let's just go into R and look at all of this R code. So the first thing I have to do is I have to put in my observed or sample data, and I do that in a column or vector of data. So I put in the colors in the order you saw them in the table. So 27, 23, 26, 34, 39, and I run that code. It makes a variable over here on the right. Oops, let me clear that out because I have something in my environment and I don't want it. There we go. And then we also want our probabilities, and each of the probabilities is 1/5. You could have put in 0.2 if you preferred. Notice it changed it to 0.2. And then we do the chi-square test before we make any graphs, before we calculate any expected counts, because we actually need to get some information out of this chi-square test. We'll come back to this chi-square test in a minute. I got my total by adding up the observed count. So I did n is equal to the sum of the vector called observed, and I run that. So my total was 149. And then to calculate the expected counts are 1/5 times n. And because I just named my sample size n, I can use n here. So n times 1/5 is 29.8. We already knew that. We did it by hand. And so I'm now going to make a vector of my expected counts. You do not have to do this. I did it so that I could get a bar graph of the expected counts. So my expected count vector is a column of data with 29.8 for each of the 5 colors. And I'm just identifying that vector over here in the environment. If we want to look at the graphs, we make a bar graph. And remember the command for that is bar plot. So this is way back from Module 3 stuff. And so you guys can go through and look at this, but I want you to see what I'm graphing here is my observed data. And I did have to ask it to do like a legend on the x-axis. So I had to put those in as a vector. So I had to put the colors in as a vector, and I had to make sure that those words, yellow, red, green, orange, and purple, matched the order I put my observed data in. So be really careful with that. And then col just stands for color. I used all of those colors. I put in a title, my Y labels frequency, my Y limits went 0 to 40, and then my X label is taste the colors of the rainbow. I'm going to run that, and I get a bar graph that you saw in our notes. Then I did the exact same thing with the expected counts. So notice I graphed the expected counts. The only thing here, you guys, you could have changed that, and instead of graphing the expected counts, you could graph the probabilities. Because again, we just care about the shape of the graph here, that it looks the same as the sample data. I prefer to do expected counts most of the time so that I can actually compare apples to apples. Also notice I got rid of the color line. Otherwise, I just copied all of this code from above so that I would get the same graph. So I'm going to hit run. And you'll notice I get the graph, except it's gray. And this uses the expected counts of 29.8 for each of the 5 colors. All right, so I have expected counts, I have both of my graphs, and now what I need is that p-value. And we got that p-value up here when we did our chi-square test. The chi-square test gives me a chi-squared test statistic. It tells me my degrees of freedom, and it tells me my p-value. By the way, I did the chi-squared test early in my code, really because we're going to need it early in the next section of notes. So my test statistic was 5.73, which is in fact what we calculated. And our p-value is 0.2201. So let's go back and look at that in our notes. So our p-value from R was 0.2201, and our chi-square test statistic was 5.73. I don't remember exactly what that was, 5.7315 from R. And notice this p-value is big. So of course we would fail to reject the null. All right, so that's it for this particular section. We're going to add on to this and do more chi-square tests.